interrupt. Please don't hesitate to interrupt if something is unclear or if I'm saying things too fast or for whatever reason. So I thought I will, my plan is to give some overview of a project I'm currently involved in. And it's a joint work with these four friends, Tobias Bartel, Dave Benson, Henning Krause, and Julia Petsova. And this is about modules over group algebras, and I'll discuss it. This is what today's lecture is about. And there is a preprint which should be ready soon. It's called, or titled, Lattices over Finite Group Schemes and Stratification. Actually, the project started a few years ago, thanks to work of I.K. Lau, whose paper, The Balmer Spectrum of Certain Deligne-Mumford Stacks, when it was appeared as a preprint. And then, there were some papers following up on this work by Tobias Bartel, which are also on the archive. And then you can see that there are, if you look at the reference list for I.K. Lau's papers, you'll see that there are papers by Bartel and also by the four of us, Benson, Krause, Petsova, and myself on this topic. Anyway, I.K. Lau's paper has appeared. And I'll tell you what these papers are about. So these are basically the basic references for my lecture. Right? As I said, there are other papers, but you can find them in the reference list to I.K. Lau's and also in the reference list to this, which should be on the archive in a few weeks, no more than 2 weeks or so. Okay, so what is all this about? So by the way, it's a rough outline of my lectures is that I will first talk about modules over, so I'll look at the first case, module representations over fields or modules over, so modules over Kg, where K is a field, where G is a finite group. And then I'll look at modules over, so I'll now go to the case of modules over, which is really for Rg, where R is going to be any commutative Noetherian ring. And I'll discuss the structures involved. And I want to spend some time discussing an example which illustrates some interesting phenomena that shows up when you look at representations over arbitrary rings. And then I'll go over and maybe talk a little bit about one of the main techniques we use, which is reduction to fibers. Okay, here's roughly the outline of my talk. So throughout, G will be a finite group. Okay, and in fact, it could also be a finite group scheme, but on this, in today's talk, I'll just focus on the group case. I mean, the results one gets for the group scheme case are the same, but somehow, the technicalities get a little bit more. So I'll just focus on the finite group case. And so let's suppose, let me recap what is already known about this and what is it we're looking at. So let's say K is a finite field. Phi just a field, not a finite field. And suppose one is interested in looking at representations of G over K. So the representations of G over K, meaning representations of G in K vector spaces, this we know is the same as modules over the group algebra of G over K. Okay, so just to warm up. So the group algebra is just a vector space spanned by the elements of the group with multiplication induced by that on the group. So I know how to multiply things in the group and you extend it linearly to this. So when you're talking about representations of G over the field K, so representations of G with vectors into vector spaces over K, you're just talking about modules over the group algebra. And this is the language I'll be using, the language of module theory. Okay, so one case, so there are two cases, so-called the non-modular case is when the order of the group, so remember G is a finite group, this is invertible. So when this is when this is a unit in the, so when it's invertible in the field, the group algebra is semi-simple. So every module is, every kg module is projective, and the indecomposable kg modules are basically the indecomposables that appear in the decomposition of the group algebra itself. So this is so-called the non-modular case, and this is there's a whole different story in this side. The character theory comes in when you can classify the indecomposable representations in terms of characters and so on. So I will focus on the modular case. On the modular case, namely when the order of the characteristic of the field divides the order of the group. So the order of the group is 0 in K. So i.e. the characteristic of the field divides the order. Okay, and for everything I'm saying, we could just, everything I say is going to be interesting and non-trivial already in the following case. So G could be the elementary abelian. So the cyclic group of order P, where P is a prime, and maybe you look at, so P a prime. So you look at C copies of the group, and K could be some field of characteristic P. Maybe even just FP, or some field of characteristic P. In this case, one is looking at modules over the group algebra. So if the group is generated by G1 to GC with the ith powers of 1, the group algebra will be because it's an abelian group, it will be the polynomial ring in these generators subject to the relations G to the P minus 1 for I equal to 1 to C, which, it's often written in this form, where you change the generators for I equal to 1 to C, where xi is G minus 1. Because you're in characteristic P, you can take the pth power inside and you see that xi to the P is 0. So it's just a truncation of the polynomial ring in C variables by the pth power. So as a ring, it's fairly simple, but it's interesting in the representation theory of this ring, module theory over this ring. And it turns out the module theory, the representation theory of this ring is already wild, except if P equal to 2 and C is equal to 2 or less than or equal to 2. So what one is looking at is not trying to classify representations, but try and understand, try and get a handle on the representation. So I will write, so again, going back to the general case, I will write mod GK, because of what's going to come later on, is for the category of KG modules. Okay. So what I was saying was this category is generally wild in a technical sense. And we want to understand rather not the individual modules or indecomposable ones, but more structural results about this category. And the standard with and since, of course, in this case too, we understand the projective modules here. The indecomposable projectives are still just the direct summands of the regular representation, which is KG itself. And so one can look at the stable module category. So this is, by definition, all modules modulo the projectives, because we sort of understand the projectives. And So the objects of this category are just objects are just KG module, finite dimensional KG modules, finitely generated KG modules, and the morphism space typically denoted this is the usual KG linear maps from M to N modulo what are called the phantom maps. So, so it's typically denoted EHMN. So these are the phantom maps. Namely maps from M to N that factor through a projective. So if you're going to kill the projectives, of course, you're going to kill all maps that factors to projectives. So this is what happens. And so this is the stable module category of course, you can do this construction for any ring. You can look at modules and kill the phantom maps. But what is special about this context is that KG is self-injective. The group algebra is self-injective as a ring. So this implies that the stable module category is a triangulated category. Is a triangulated category. If you wish, you could also think of it as the quotient of the bounded derived category by the perfect complexes. So this is what is sometimes called a singularity category of the group algebra. Okay, but I said something and wrote something else. This is a triangulated category. But in fact, what the notation is suggesting is that this is even tensor triangulated. Tensor triangulated, where the tensor product on the category is the tensor product over K with the diagonal G action. So by which I mean, if I give 2 KG modules M and N, you can look at N tensor N, but then you want to view it as a G module where G acts on, say, a pure tensor by tensor Gn. So this is the definition of the action. This is called the diagonal action, and this makes this into what is called a symmetric monoidal or a tensor triangulated category. Okay, so once you have such a thing, this falls into the realm of TT geometry in the sense of Balmer, and you can ask for the Balmer spectrum of this, and this is a theorem due to Benson, Carlson, and Ricard. From 1996, that the Balmer spectrum of the tensor triangulated category is the proj in the sense of algebra geometry, commutative algebra of the cohomology ring. So I should say, so here, this is the cohomology ring of G, which can be computed as X of the group algebra where K is viewed as a trivial representation and proj is the usual. So it turns out because G is a group, this algebra is graded commutative and it's finitely generated, hence Noetherian. So you can look at the homogeneous prime ideals in this and look at the irrelevant one, throw away the irrelevant one, namely the positive part of this, which is a maximal ideal, and you get the proj. And the Balmer spectrum of this category is the proj of this cohomology. Of course, when Benson, Carlson, Ricard proved this, the Balmer spectrum didn't exist as an object. I'm just recasting their result in terms of the modern language. What this is tantamount to is basically a classification of the thick ideals in. So this is a classification of the thick ideals in the stable module category. Okay. So this is the result from Benson, Carlson, Ricard. Of course, there's a long story that concerning such classification results, and this result was inspired by work of Niemann in commutative algebra and Hopkins in chromatic homotopy theory. Okay. Now, this result can also, so already in the work of Benson, Carlson, Ricard, although the problem or this question and the statement concerns the stable category of finite dimensional representations, it was important to consider also all representations. So you can look at the big mod, so all KG modules, so all representations, not just the finite dimensional ones. And you can look at the corresponding stable module category. So again, this turns out to be a tensor triangulated category, and it has, so with the same tensor structure. So this is even a compactly generated and it's a compactly generated triangulated category. And the compact objects are the finite dimensional ones. So when I write C, this is equivalent to the small. So by this I mean the compact objects here. These identify with the finite dimensional representations. And even if you just want to understand the finite dimensional representations, it's helpful to work with this bigger category. And in fact, Benson, Carlson, Ricard, the proof that that was given did operate in this category. And so what we proved, so this is now Benson, myself, and Krauser. This was around 2011. And I should also mention work that we did with Yulia Petsova in the case of finite group schemes around 2017, that the lattice of, so there's a bijection between the localizing ideals in, so the theorem is that, roughly speaking, what it says is that there's a bijection between localizing ideals in the fixed category and again proj. Oh, here I should, oh yeah. So let me just write this and say and proj, subsets of AG. So there's such a bijection here. And so between these two sets. So it's saying that the localizing ideals in this big stable module category are parameterized by subsets of proj. I should say here, this classification due to Benson, Carlson, Ricard, this computation of the Balmer spectrum is saying that the thick ideals are in bijection with the specialization closed subsets of proj, whereas this is saying that the localizing ideals correspond to arbitrary subsets. And this does imply, you can't recover the work of Benson, Carlson, Ricard from this, okay? Okay, so of course,
Sorry,
yeah.
Srikanth. Can you remind the notion of localizing ideals?
Yeah, sure. So suppose you have a TT category. So say a big TT category. So not so and so a subcategory is localizing if it's closed under if it's a triangulated category closed under arbitrary sums. Subcategory closed under all coproducts in the category, right? And it is said to be an localizing ideal if it's also closed under tensoring with objects in T. So it's also closed under tensoring with X for all X in the category. So just like an ideal in a ring is a subgroup which is closed under multiplication by any element in the ring, a localizing ideal is a subcategory which is of course closed under sums, but also multiplication by objects in the big category. Not just things in S, but for all X and T. So this is a localizing ideal. So it's the analog of ideals in a ring. So the result is that the localizing ideals here correspond to. So maybe here I should mention that if you're looking at P groups like the ones here, elementary abelian P groups, where the trivial representation generates the category, you don't have to worry about this. This condition is automatically satisfied. But otherwise, you do have to care about this. Okay, what I was going to say was this is not some abstract bijection. This bijection is given by support theory. Meaning, for each module M, each representation, you can associate a subset of Proj. Yeah, this is so-called the comma. This is sort of the variety associated with M. And there are many there are at least 2 or 3 descriptions of this variety. When M is finite dimensional, you can think of this as the variety in terms of annihilators of cohomology of M. Otherwise, the definition is a bit more complicated. But anyway, this bijection is not just an abstract bijection between sets. It's realized by the map that associates to each representation the variety of M, or the support of M, which is a subset of Proj. Okay, let me not go too much into the details of this construction. Okay, so this is all old story. And I should say that, the point of these results is that they're actually useful in studying representations. It's not an end in itself. You can take this as a starting point for trying to understand the representations. For example, these sort of results play an important role in Carlson's and others' work on classifying these endo-trivial modules for groups and so on. Okay, now let me come to the topic, the main focus of my talk, namely.
Then you restrict it by this bijection to the smallest stable mod. Then is it interesting?
Which one?
The restriction of this map to the smallest mod. Yeah, this map.
Yeah, you get this one. Then you get a computation of the Balmer spectrum. If you restrict it to. So that's why I said that this result implies the BCR.
Yes. Okay. Thank you.
Yeah. So what I was going to, so let's say now that R is any Noetherian commutative ring. So you can think of, actually you could think of the integers or any polynomial ring over a certain number of variables, finitely many variables, or their quotients. And one is interested in representations of, so the focus is now on, so you still want to look at representations of G over R, but the focus is on lattices. So by which I mean, so, and this is the lattices of G over R. So by which I mean finitely generated RG modules that are projective as R modules. So you're not looking at all RG modules. Only those that are projective when you restrict to. So the group algebra is RG, and R sits inside it as a subring generated by the unit. So you're looking at modules over RG, which when you think of as R modules, are projective. So there's a long history onto looking at this category of lattices. In fact, this goes back to work of Brouwer already. If one is interested coming, for example, from number theory, one often looks at Galois groups or representations of Galois groups, but over, say, some ring of algebraic integers. So there is quite a lot of literature on this category of lattices. So one wants to understand, perhaps along the same lines as what I've been discussing before, what happens when you look at this category of lattices. So I want to tell you a little bit about this category, but actually much of this basic discussion can be abstracted as follows. So what's happening is that we have a Noetherian commutative ring, and we have a R algebra, which is finite, meaning finitely generated, and projective as an R module. Okay, so of course the group algebra is one example, but clearly there are many more, right? You can imagine there are other examples too. So if, for example, R is a field, I'm just looking at all finite dimensional K algebras. So that's quite a vast. So in this case, again, what one wants to look at, or what I want to look at, is mod AR. So A modules of which are finitely generated and projective, as before, finitely generated and projective as R modules. Now it turns out that so this is of course no longer an abelian category, but it is an exact. So you can look at all A modules. So this is an exact subcategory in the sense of Quillen of the category of A modules. It's not abelian because if you have an exact, if you have a map, if you have an injective map between modules here, the co-kernel need not be in that category because co-kernels of maps between projectives need not be projective. And neither do kernels. So I'm only looking at modules that are projective when you restrict to R. And I'm looking at the exact structure that's inherited by this when you view it as a subcategory of mod A. So you're looking at only exact sequences where all three terms are projective over as R modules. So this is an extension closed subcategory of mod A. So it does have an induced exact structure. Okay, so it turns out that one can identify the projective objects in this category. So the projective objects of this category are precisely the projective A modules, namely the additive subcategory generated by A, and the injective objects in this category coincides with the additive subcategory generated by what is called the dualizing bimodule, where is forms of the dual of A. Okay, so this is not very hard to check. So we understand the projective injective. Remember, projective injective with respect to this exact structure. So it only, so once you have a category, then once you have an exact category, you can talk of projective modules. Now, by looking at lifting properties with respect to the exact sequences, subject admissible epimorphisms in the category, and also injective objects. And it turns out the projective objects are precisely the projective modules, and the injective objects are the ones which are direct sums of finite copies of omega, which is the dualizing bimodule. Okay, so this then suggests the following definition. So we say that A over R is a Frobenius, so A is a Frobenius R algebra. Yes, R algebra when omega is projective. Okay, so this is when the dualizing bimodule is projective. This is equivalent to the statement that because there is actually some duality going on here, this is the same as saying that the projective modules are the same as the injective modules for this exact structure. Okay. So this is a notion of a Frobenius R algebra. Again, this is nothing new. This goes back at least 50 years. I've seen this definition in papers of Shea and Stoic from 1970s, but I'm sure it goes back earlier. So you say that A is a Frobenius R algebra if these two coincide. So this is tantamount to saying that mod AR is a Frobenius category, Frobenius exact category. So it's always an exact category. But this condition is tantamount to saying that it is a Frobenius exact. And the point about having a Frobenius exact category is that you can, when you can look at you can do exactly the same construction as we did earlier for groups, so you can factor out by the projectives. So this is by definition mod AR modulo the projectives. Just which is of course just I should have said it's by which I mean let me write add A. And it turns out that the Frobenius property means that this is again A over R of Frobenius. Implies that this is a triangulated category. Just like in the case of finite groups. So this is the import of having a Frobenius exact structure. You end up with a triangulated category. Then again, you can ask for the thick subcategories of this category and try to understand its structure from that perspective. Now, for now, I focus. So as I was saying, one can also consider the big category, and the reason for doing this is again because once you work on even if you want to understand only the finitely generated ones, so this will be the stable category of so A modules, all A modules, not just the finitely generated ones. But again, the condition is that projective over R. And once again, this is a triangulated category. Okay. Now, already here, one runs into a question. So I don't know that this is compactly generated. And actually, okay. So what we have is that we have this. So we have this category we have this big category, the stable category of all A modules. And sitting inside this is a stable category of the finitely generated ones, again, which are projective. So these are certainly compact here, but I don't know if these are the only compact ones. So in any case, we can look at, it's certainly true that these are not the only compact ones. So it could be that, and I know that there are more. So if you look at, so what you can do is instead is look at the localizing subcategory generated by this. So let me call this, I'm introducing a new thing here. So this is the localizing subcategory, the smallest localizing subcategory generate of the big stable module category generated by the finitely generated ones. Okay, so then the subscript LF is for the locally finite category. Locally finite part of STAMOD. Okay, so let me reiterate. I don't know that this is compactly generated. I do know that, but I do know that these sitting here are compact. And therefore, what I can do is I can look at the smallest localizing subcategory that contains this one, which I'm going to call the locally finite category. And it's just by construction, it's clear that this is compactly generated and that its compact objects are precisely, there is a small, okay, so there is a small subtlety here. Let me say this. So this is a compactly generated triangulated category.
Is it algebraic? Can we see?
Yeah. This is because you're coming from an algebraic one. This is already just modules over this thing, right? And it has generators. Yeah. So this is a compactly generated triangulated category, and the compact objects is basically the thickening or the closing this up on the direct summands. So this may not be idempotent complete. So it's the idempotent completion of STAMOD. Okay. So this already raises a question. So if I give you a module in AR, how do I recognize, given, so this is this, how do I recognize if this is in the STAMOD? How do you know it's locally finite? Right? So how to recognize? Objects or modules in AR. Because it seems that this is it's clear that this is sort of the interesting category if you were interested in understanding lattices over A. And by the way, there are other constructions that naturally lead to other perspectives that lead to considering this. This is what is called the end completion of this, or a certain DG enhancement of this. So from various perspectives, this is the right category to consider when you look at A modules that are projective over R, and you would want to know, if you're given a module that's projective over R, so something here, is it in this category? So I can offer one result in this direction. So this is a theorem that when R is regular, so it's a condition on R, not on A. then every module is locally finite. So at least if you're looking over, say, over the integers or the polynomial ring or something, you don't have to worry about the distinction between these two. You can take any A module that's projective over the base, and that will be locally finite. But this inclusion the inclusion can be strict in general, and that brings me to the third part of my talk. I see that I'm running a bit slow, but that's okay. So I want to give an example where the inclusion fails, right? So the example is actually quite elementary. So let's take kt over t square, where k has characteristic 2. So k is a field. And let me assume for simplicity that k is algebraically closed. This will come up later, okay? And I should have mentioned here, when I'm talking about Frobenius algebras, of course, the main example is that RG itself, the group algebra of a finite group, is Frobenius. And then I want to take for the group the simplest possible group, namely the cyclic group of order 2. Okay, so then I'm looking at R, which is RG. So this is my Frobenius algebra A. And it turns out, again, by the same sort of substitution, this is isomorphic to Ex by t squared. So I'm looking at modules over this truncated polynomial ring that are projective when you think of them as projective as R modules, when you restrict to R. Now, as you see, you can identify mod A with mod of A, you can identify with modules over the group, elementary abelian group of rank 2 with coefficients in K, because we talked about this before, that the group algebra, you recognize this as a group algebra of an elementary abelian 2 group. Okay, so these are all the A modules. And then you can ask, if I give you an A module, what are those? How can you recognize those that are projective and restrict to R? And here again, you can use variety theory, the cohomological variety theory that I mentioned. And that tells me that the things in fact, I can even look at the big one once and for all. Either it's the same for little a or big A. All A modules. And the modules that are that become projective with when you restrict to R, these are precisely the modules, A modules, such that if you look at, so let me call this group E. If you look at the variety of M as an E module, this doesn't contain the point 0, 1. Let me say a bit here. So if you look at, so maybe I should preface this with a comment. So if you look at this group A, the cohomology of the group is just is a polynomial ring in 2 variables. We call them eta 1 and eta 2, corresponding to sort of T and X, where these have degree 1. So the proj of this cohomology ring is just P1, the projective line over K. So basically, it consists of points A, B. You can identify it with, so the close points are, these points A, B, where not A, B is not equal to 0, 0, not both are 0, union the generic point, namely the point corresponding to the 0 ideal. So the homogeneous prime ideals here are basically the zero ideal and the maximal ones, because it's it's a graded ring of dimension 2, and because I'm assuming it's algebraically closed using the Nullstellensatz, you can see that the height 1 prime ideals here are precisely parameterized by points, tuples like this. So this is just P1, and then from this, in terms of this description, the A modules that are projective over R are precisely those for which the point 0, 1 is not in the variety of M, not in the support of M. So the proof of this uses an interpretation. Proof uses an interpretation of the varieties in terms of rank varieties. John Carlson's rank varieties. If you think of variety theory in terms of rank varieties anyway in the first place, and this is just by definition almost, that the modules that are here are precisely those that for which 0, 1 is not in the support. Now, so let's now look at so we have this. So we have the stable module category here. So we have the stable module. So let me write it. So we have the stable module category of AR, which, as I said, they correspond to modules in M, the usual stable category of this elementary abelian thing where 0, 1 is not in the variety. And I'm interested in understanding what are these locally finite ones. And sitting inside this are this small stable module, AR. So of course, this has the same description. You're looking at finite dimensional modules. So this is M, the small categories, finite dimensional representations of E, with the property that this point is not in the variety of M. But but the key point is, but this is equivalent to saying that the generic point is not in M. And this is because the variety of M is closed. If you start with a finite dimensional module, the variety of the module is closed, is a closed subset. This is a risky topology. So it cannot contain the generic point because the closure of the generic point is all of P1. So if it omits any point in the variety, it must also omit the generic point. All right. So now if you look at modules that are built out of such things, for those two, the building process is something like an addition. So for those two, these 2 points must be omitted from the support. So this sort of shows that these are precisely the modules of a stomod, such that not only is 0, 1, but also the generic point are avoided from this. So this shows that this inclusion is strict, because here you're looking at throwing away 1 point from, throwing away 1 point from the support, and here you're throwing away 2 of them. Okay, in this example, it's quite clear that these 2 categories are different. And in fact, you can construct explicitly a module which is here and not here. In terms of a commutative algebra geometry, when you're looking at a complement of a point, this is a closed point. So you're localizing away from a closed point. So you're looking at an open subset of P1, which is the complement of this closed point. So this one here, this is is a localization of this away from the close point 0, 1. So in this case, the big stable module, this is also compactly generated, and I know the compact generator. And one can say quite a lot more about this example, and maybe I'll get back to it, but given that I'm running out of time, let me go back to the story we were looking at. So we were looking, so
yes. Does it make sense to think that the last theorem is if and only if?
Where?
Just about, yeah.
This I don't know.
The regularity characterized here.
Yeah, that's a good question. I don't know.
Yeah.
It may be. So, I think it's quite likely that you can, I can think we can prove that it's if and only if. By choosing an appropriate group. I don't know though. The short answer is I don't know. It's a good question. So let me go back to this this general context. So we want to understand, especially in the case of a finite group, this category, the big star mod and locally finite ones, and in particular the small star of AR. And to this end, so the basic technique we use in our work is this reduction to fibers. What do I mean by this? So if you look at P in spec R, okay, and let me say Kp is the residue field at P. So it's the localization of this. So this is also, you look at R mod P, which is a domain, and you invert everything outside P. It's the field of fractions of R mod P. And then you can look at the functor from, if it tensor, you can tensor with, and this actually goes from the big category itself to a mod, let me write it as AKP, KP, where I send a module M to its fiber over P, which I'm going to write as AKP. Okay, so what's happening is that you can think of A as a family of rings parameterized by spec R, and lying over each prime P is this ring AKP, which is A tensor RKP, which is now a finite dimensional algebra over the field Kp. So as P changes, of course, the field changes. So you can think of A as a family of finite dimensional algebras parameterized by spec R. And one is trying to understand the whole category by looking at what happens. So looking at these, the categories over each prime P. And so one of the basic, so for example, already has a theorem which tells you that you can try and get some information about this category by looking at all its fibers. Here's a fact that A is a Frobenius R algebra. So the theorem. This actually already goes back to Shea and Stoic. So let's say A is a finite projective R algebra. Then A is a Frobenius R algebra. If and only if the fibers are all self-injective. For all P in spec R. So this really says that this is sort of the global analog of the self-injective algebras. So this is one illustration that you can say, the fibers do control something about the global situation. So as I said, this is already in Shea and Stoic from at least there, maybe earlier. So here's another result, which is in our paper, which is yet to appear. And this is important in our work, so I'm bringing this up. So suppose you take a module, okay, take any A module that is projective over R. And in this variety theory business, you would want to know when M is projective, because after all, you want to, when you construct the stable category, you factor if and only if all the fibers are projective. So these are projective for the fiber, of course, for all P in spec R. So you can detect projectivity in terms of the fibers. So by the way, this result is not so difficult to prove when M is finitely generated, but it's important that it also holds for any A module. So you can detect something being projective over the fibers. And you're building on this. So now let me go back to, let me go back to the original problem I started. So back to G, a finite group. And we are looking at, so we were interested in the stable category of, I know I've run out of time, give me a couple of minutes and I'll wrap up. So we are looking at the stable category of lattices and also the big category. So everything I've said so far applies to these two categories. And the main result of our work is that we can compute it turns out that these are also tensor triangulated. Tensor categories, where now the tensor product is over R. I don't have to worry about taking derived tensor products because all the modules are already projective over R. So you can take tensor product over R with a diagonal G action. Okay, and then you can ask about, so again, you end up with a symmetric monoidal category, a TT category, and this is sort of the big analog. And the main result of our work is that you can parameterize, let me say it like so, that the stable category is stratified by it's the cohomology of G with coefficients in R. And by this, I mean that basically it means that there is a bijection, that there is a support theory which gives you a bijection between the localizing ideals in this category and proj of this. And as a consequence, as a corollary, we get that, that the Balmer spectrum of a small stable category of lattices, this is homeomorphic to proj of the cohomology ring with coefficients in R. Okay. So one has exactly the same result when you replace the field by any R commutative ring. But the key is, of course, that the category you're considering is this locally finite category, which is the one interesting thing that comes up. And the proof of this is also this reduction to the fibers business. You can, in the case of a finite group, when you look at this side, you're just looking at the representations of the group over this field KP, and then the results of Benson, Constant, Ricard, and my own work with BIK and E apply. So we know the story, the level of the fibers, and the problem becomes one of patching that information to get something about, to deduce, to understand the structure of this. And the entire paper is really devoted to this, understanding this reduction, or this reduction to the fibers business. Because, to understand this, we have to understand, first of all, both sides. When you reduce to the fibers, we want to understand we want to understand the connection between the stable category over R and the stable category over the fibers, and also understand the relation between the cohomology ring over R to the cohomology ring over the fibers. And this is really where the bulk of the work comes in. And I should maybe say go back to this example. I'll just talk through this. As I said, this example is discussed in detail in the paper. So if you look at this example, if you view it as, if you view this as it is a localizing subcategory of this stable category of representations over E. So from that perspective, we understand all the localizing subcategories here. They are parameterized by basically points in P1 except these two, right? So these are all the closed points of P1 except this special point. So there is uncountably many, no, well, depending on the cardinality of K. It depends on the cardinality of K bar. You know what the localizing subcategories of this are, okay? So they're definitely not, there are infinitely many of them. But what our theorem says is that if you think of this as a TT category, then the proj of the cohomology ring here is easy to compute. So here, it turns out, if you compute the cohomology ring of A with R, so RG, R, it just comes out to be a polynomial ring in one variable. This is an easy computation. So this is, computing X RG RR. So that tells me that there's only one non-trivial prime ideal, irrelevant, only one prime ideal of consequence here. So which tells me that there's no non-trivial localizing subcategories. So although there are localizing ideals, so although there are infinitely many localizing subcategories, there's only one that is a localizing ideal. Okay, so this is an interesting phenomenon that shows up. And in the paper, we just discuss more about this and say a bit more about this. But maybe I should stop now, given that I've already gone over time. Thank you.
Thank you very much for your very nice talk. Are there any questions?
May I ask one?
Yeah, sure.
Yes, please.
First of all, I would like thank you for your nice presenting. You have a result that mentioned by Jawad about that regularity implies something.
Mm-hmm.
And the other one that you have a two-sided result for Frobenius algebras. Is it possible to be hopeful for a similar result for something like Cohen-Macaulay rings, maybe order algebras?
Oh, wait a minute. You mean something like this?
You have, this is one direction, and also you have a result about Frobenius, a characterization for Frobenius algebras.
Oh, this one.
Yes, that's true. So at this, I can, for myself, I consider Frobenius as somehow similar to Gorenstein rings.
Yes.
So
Yes,
is it possible to have a result like this for
so,
Cohen-Macaulay rings or order
hang on. Here,
algebras?
R can be anything. In fact, here R can even be, need not be Noetherian even, but it is commutative. So this result, this characterization of Frobenius algebras doesn't require anything about R. It's really a relative situation. It's saying, so this is actually, was it Kamran who was speaking?
Yes.
Yes. So
nice to see you at least online after
yes, at least online after many years. So this is really a relative story. This is talking about, so where did the picture go? So we're looking at this. So this condition about being a Frobenius algebra is saying this is a Gorenstein map. So it's saying the dualizing module is projective. So it doesn't depend on R. It's only a relative property.
Oh, yes.
this aspect. So it's not important. I'm not saying R needs to be irregular or anything. It's just a property of the Gorenstein maps. So actually, Buchwitz has looked at this context much more generally. So here I'm looking at Frobenius algebras. We might also look at, so Frobenius algebras are, so if you look at this, where is that characterization go? Shea-Stoic. So Shea-Stoic proved that this is Frobenius if and only if the fibers are self-injective. So of course you can ask what happens if self-injective means Gorenstein of dimension 0, virtual dimension 0. So you can also ask what happens if these are just Gorenstein algebras. And this is the thing that Buchwitz studies in his manuscript, the maximal Kornmark, the famous one, the maximal Kornmark-Collie modules, etc. So far, this theory is only about, but then in that case, you would want to reduce, you would want to, so maybe that's one direction to look at. We have not looked at that. We are looking at basically this class of examples because our main concern was to understand this sort of stratification results and really outside the case of groups and some other special finite dimensional algebras, I don't know stratification more generally. I don't know if that answers your question, but somehow tangentially related comment.
Thank you.
So are there any more questions?
Just a very general question. In the definition of lattices, you consider finitely generated RG modules that are projective as R module, yes?
Yes.
What about if we consider the finitely generated RG modules that has, for instance, projective dimension at most 1, for instance? It's still exact, I think, exact subcategory.
It's still an exact subcategory, yeah, I see. I wonder if, so I have a feeling, I don't know, but my sense is you will not end up with a, so what would you be killing? I have a feeling I have a feeling you would end up with the same story when you stabilize things, because when you stabilize things,
no, projective dimension at most 1, not only projectives.
I know, but when you go to the stable category, see, when you go to the stable category, you would not so you're allowed to replace a module by its syzygy, right? Because you're killing the projectives, roughly speaking. So if you had finite projective dimension, by going to a high enough syzygy, you can end up with something which is projective over the base, because as long as, and in fact, that is sort of what is going on when you have a regular ring. That when you have a regular ring, you can replace anything by a high enough syzygy and obtain something which is projective over R, which is sort of what is behind the statement that over a regular ring, these two categories are the same. Yeah. So what I'm saying is maybe as an exact category, it will be different, I suspect, but I don't know that it will be Frobenius exact. But in any case, I suspect if you stabilize it, when you kill the projectives, you'll end up with the same category. You could also ask this for modules of finite projective dimension, right? You can say, look at those of finite projective dimension. But I suspect when you stabilize things, you'll end up with the same story.
Yeah.
I don't know. That's my suspicion.
Thank you.
Any more questions or comments? I have just one question. In your results, you say some results about the projective objects in A and the projective objects in the fibers.
Yeah.
Are there any similar results for the indecomposable objects? I mean, or about the type of representation type of the algebra, for example?
That's a nice question. So I see. Indecomposable, I don't know that. Yeah, that's a good question. So I don't know. So as I said, this business of trying to understand a module category by looking at the fibers seems interesting. And the whole paper really is various results about how you can reduce various questions to this, but we have not looked at the representation type. Also, I don't know how much one understands the representation type as is understood in the context of finite dimensional algebras over general Noetherian commutative rings. I don't know if there is.
I mean, is it possible, for example, by the control the fibers? I mean, the type of the fibers. It's possible to control the whole algebra, the representation type of the whole algebra, maybe.
So you want to? That's what you mean to say. That can you control this in terms of this?
Mm-hmm.
So let's be careful about one thing. Suppose you just look at the case A equal to R, right? If you just look at the case, then the fibers are just fields. So in some sense, the representation theory is very simple, but you're not.
Mm-hmm.
But when you're looking at R modules, of course, I'm only looking at projective R modules. But they are already quite a complicated story, the projective R modules. But still, but I don't know if there's anything more complicated than that can come in. So that's one good example to keep in mind, just the case A equal to R. You don't expect to say something about all A modules, only about those that are projective over R. And this is also sort of the distinction between the global, local, and global story. So if you, if you take a projective module over the fibers, it'll all become free, but it will not be free. So you could have non-trivial projectives which are all free. So the fibers don't retain all the information, but they do retain and some, yeah.
Oh,
So
thank you.
Yeah, okay. But that's a good question about representation type. I don't know.
So thank you for your very nice talk.
Thank you.